Here we will introduce this abstract concept of a vector space. It's a usual mathematical game to have something which works well and then try to replicate it any way you can. That is this abstraction process. And the thing which works well in the model for all this is the coordinate vector space. That is the set of vectors of a fixed length by default with real coefficients. And what is important for the linear algebra we used it so far is that we can add these vectors and we can scale them, multiply by numbers. And that's what is generalized, that is what is taken to be an abstract vector space. So a vector space I'll call it V, and to be completely precise, I have to specify what is a set of scalars. Scaling in coordinate vector space is natural with what the coefficients are, so with real numbers if it is a real vector space. But in general, we could change the arithmetic of our linear algebra to any so-called field. So that will be done later. I will talk about fields in the next meeting. And the general definition will be just what is to be to appear here, but with real numbers replaced by an arbitrary field. So what is a vector space? So first of all, over real numbers. Well, it is a set, as in here, of what we then call vectors. What makes them vectors, what makes the set a vector space, is the ability to add vectors and to scale them. So that is the following two next things. The operation of addition, taking two row vectors and adding them one to the other if they have the same length, is this addition for coordinate vectors. In general, it is just some operation which we can define. It takes two vectors and it produces one which we call the sum. And the second operation we have on vectors is the scaling or scalar multiplication. Or multiplication by scalars. And that is feeding on a real number and a vector and producing a new vector. So if we have a real number C, a vector called V, the result is C multiplied by V. That is not all. What is important is that these operations are not arbitrary, but playing the game of usual addition and scaling of coordinate vectors. And these rules which operations have to satisfy, called axioms of an abstract vector space. And the first such is associativity for addition of vectors for taking the sum, because it's just coming from associativity of numbers which are coordinates of those three vectors. We need to have three vectors to see this associativity in action. It's just doesn't matter in which order we will perform the addition operation on three vectors. To add them all, we have to add one pair and then to add a third one to the result. And it doesn't matter how we do it. In these two ways, the result will be the same. Then we have commutativity of addition, which says it doesn't matter which one comes first and which is second. For two vectors, the result of addition is still the same. Then for scalar multiplication together with addition, we have two distributivity properties if we look at scaling operation and addition operation of coordinate vector spaces. Now we want them to be there, we make them axioms. This is one distributivity where we have one number and we're scaling with it a sum of vectors. We can write the result as a sum of two scalings with the same number. Or we could have two numbers and we could compute their sum and scale a vector with it. And that will be again a sum of two scalings of that same vector with different coefficients. And finally, we have associativity for scaling. If we have two numbers and we scale with one and then with the other in a sequence, it is the same as to multiply first numbers and then scale with the product number. And that is not all. The last two are special conditions that when we scale with zero coefficient any vector, the result will be what we will call zero vector. And then when we scale with coefficient 1 any vector, the result will be that vector with scale. So this is just one answer for all these if the coefficient, scaling coefficient is 0. That is an unusual way of presenting axioms. Usually there are more of them, like negation and all that, but I'm claiming that this shorter list of axioms is still enough to conclude that, say, we take zero vector and add it to any other vector, the result will be that other vector, and it doesn't matter. That is just commutativity. It doesn't matter which order we add this. It will also imply this set of axioms. If we take -1, the number, real number, scale the vector, we will have something which might just call -v, and then the property of this -v will be such that when we add it to itself, to v, the result will be the zero vector. And again, doesn't matter in which order we add -v in v. So that is, of course, very straightforward, very trivial for coordinate vector spaces. Addition of vectors and scaling just satisfy all these properties. And that, of course, makes the first example. But no surprise, because we model the definition by this example. More interesting examples of abstract vector spaces, but still very concrete, are solution sets of a homogeneous linear system. And that solution set will be some subset of coordinate vectors which are all solutions, which each of them solve a concrete homogeneous linear system. And then we checked that some of this of any of these solutions will be a solution, and scaling of any of the solutions, if the system is homogeneous, will be again a solution. So that is an example of something which is called a subspace. Subspace is something sitting in already vector space. In this case, the vector space is a space of coordinate vectors with as many coordinates as unknowns. So unknowns are these coordinates of a coordinate vector. In general, we could just have a subset of an abstract vector space, and it will become a vector space in itself, and that is what is called a subspace. So to see that something is a vector space in itself, is a vector space with the same addition and scalar multiplication as we have for vectors in V is easy to check. It's just three properties which have to be there. So the first one is that if we have two vectors in a subset, then their sum has to be. Second is that the zero vector, the special vector we have here, is in a subset. And the third one, not surprisingly, if we have a vector, I'll call it U, then negative U, this vector, is also in a subset. So then the subset will be a vector space in its own right, and it's called a subspace. That's what solution sets of homogeneous systems are. They are subspaces of a coordinate vector space. Then next example again, which we have came about is let's fix two sizes M and N, and let's look at matrices with real coefficients of those dimensions. And then we know how to add matrices, and we know how to scale them, multiply by numbers. Doesn't matter the sizes, we can always scale all the entries in the matrix, multiply by number, and that what will make it a vector space. It's not much different to coordinate vector spaces. Instead of a line, our set of numbers is written as a table, as a rectangle, but we still can imagine straightening this rectangle in a long line of length m times n. It can be done in many ways. We could read row by row, or we could read column by column, or any other interesting way. But all in all, we will have m times n coordinates in this effectively coordinate vector space. But more generally, these are the same things as we saw also as linear maps between coordinate vector spaces. So multiplying vectors by matrices of those dimensions, we can see them as linear maps, turning column vectors of length m into column vectors of length n. So more generally, if we look at a set of linear maps from a vector space U to a vector space V, so again, what is to be linear? It is to be preserving, as it is called, addition, so being additive, and being transparent to scaling. This set of linear maps, we can make a vector space by introducing the operation of addition of maps and scaling of maps. So when we have two maps, we can say that the sum is again a map starting in U and turning U vectors into V vectors. And the way it is done is we just use F and we use G. We know how to apply them to any vector, and then we can take these two answers in V and compute their sum. And that will be in U map from U to V. And that is what will be addition for functions, for maps. Scaling a function, again, we can completely describe a function by telling what the values of that function are, and the value of that function c times f on the vector will be this value, which is a vector in V, and hence can be scaled with the coefficient c. So these are the two definitions. Checking the axioms for these two operations of addition and scaling is an abstract but still an interesting exercise. And that will make the set of linear maps a vector space. And in particular, it will correspond to our standard addition and scaling of matrices. So finally, a sequence of examples, which again we will deal mostly with later. They are functions. vector spaces of functions. Have to be restrictive with what functions, what the values of functions are. So if I want a vector space of the real numbers, the values have to be real numbers. And the easiest kind of vanilla case of this vector spaces of functions will be just functions without any restrictions, without any conditions put on. So just all maps from a set to real numbers. It will be the set of all functions. Into real numbers. And again, if I want to make it a vector space, I have to say what is the operation of addition and what is the operation of scalar multiplication, and I need to be sure that these two operations will satisfy the required axioms. So the operation of addition of two functions is just we had it for linear maps on any element. Now we don't do, if you look at this way we define the addition, we don't do anything with the input. We don't add it to anything at all. So now it is crucial because X is not a vector space, it's just a set. And this point-wise it is called addition is still working pretty well. And point-wise scaling is what we use to define the scaling of function. This new function, old one scaled by constant, is taking on an element x, taking this value. Again, it is an exercise to check that these two satisfy all required axioms, making the set of all functions a vector space. What is good about this is that we can look at interesting subspaces in this set of functions, put in some restrictions, put in some conditions on functions, like continuous. Continuity condition will be closed under the addition, pointwise addition and scaling, saying that really that sum of two functions, which each of them is continuous, will be continuous. Zero function will be continuous, constant functions in general. If a function is continuous, negating it will still make it continuous. Or rather, I should say, I'm sorry, I'm asking too little. I should really ask that instead of the second one and the third, I should ask that for any number, scaling with this number is in U. Before it wasn't really enough to make it a vector space, because if I would just scale with 1/2 and somehow will miss my U subset, then it won't be a vector space. But yeah, any vector and any number should produce a scaling which is inside the subspace. So continuous functions are like that. If we scale them with any number at all, that becomes redundant, by the way, because scaling with zero vector, we will get the zero vector anyway. Scaling with zero number, rather, we will get the zero vector anyway. So continuous are like that. Differentiable functions, functions which have derivatives. But one addition, so to make sense of continuous, x has to be something which has what is called topology, really. But the easiest example would be just real numbers again. So continuous functions on real numbers, just as if as they are defined in calculus class. Differentiable again in the ordinary sense. Will be closed under addition and scaling. Spelling it out, the sum of two functions which we can differentiate will be differentiable. The derivative of the sum even better, we can give the answer for the derivative. It will be sum of derivatives. And the derivative of the scaling will be just the scaling of the derivative. So taking derivative is a linear map. And putting more conditions like infinitely differentiable infinitely many times, or even better, polynomial functions, all still be examples of these subspace things. So they will be all closed under addition and scaling defined in this pointwise way. And that is it for the first appearance of abstract vector spaces.